Good afternoon, everyone. This is Astro 10 Online, Celso Batalha, Monday, March 27. Few things about this week class. We do have a midterm coming up on Thursday, and please be aware of that. I will send some reminder notes, but we never know. And if all goes according to the books, and on Saturday I will open again, certainly not the same video, but a smaller version of it, or perhaps the same number of questions but different questions. This is on Saturday. So, and I recommend you to do both, and I will collect the highest score of both. Again, those questions are critical thinking questions. You should know your subject. It's not something you can quickly find answers in Wikipedia or on your book. So you must know the subject. And the main focus here is pretty much light and solar system formation and pretty much what we have been studying before. Okay. Now today the subject is measuring stellar properties. It's a fascinating subject and has all to do with the applications of what we learned in chapter 4 with respect to light. One of the main points of discussions that I have emphasized in the last 2-3 weeks is that although we do not bring to laboratory the objects we normally study in astronomy, like quasars, galaxies, they are too big, first of all, to be in a laboratory. But we don't bring pieces of it and open up and dissect like we would do with any other object in our planet Earth that can be directly studied and directly touch it. So we can't touch this object. So how do we know so much about them? And we can talk with some authority and with some confidence that we are not dreaming and we are not doing science fiction. Well, we know because of light. So light is a energy, is a electromagnetic radiation, is an energy that is propagating through space, and as it interacts with matter in the way we learn in chapter 4, it gets slightly changed in its characteristics. So perhaps some of its intensity at certain frequencies are changed because of this interaction, and we call those changes fingerprints, and they are pretty much absorption or emission lines. So the subject is fundamental because we can point a telescope to stars and find their properties, and that's going to be the main topics of of this week class. First, I would like to open up the Astro News number 4, The Seeds of Science Skepticism. This is an interesting article, and I would like you to read it, although it has not a direct correlation with what we are doing this week, but it touched some important point in science. I mean, scientists should be skeptical. I mean, when new information come by, you should be able to criticize it based on facts that you have available. And skepticism is what makes science grow. And in some contexts, especially in the religious context, skepticism is not something welcome. I mean, if there is some dogma or some point of faith that you should follow, a tendency is within the realm of religion, skepticism is not there. It shouldn't be there. In the realm of science, it has all to do with science. But the point of the article is not only to discuss skepticism, as it is important in science, but why even people who tend to be educated and seem to have a good understanding of science and the workings of science, they tend to, if you have a series of information around, you tend to highlight those that benefit your worldview or your interest, and information or data that does not support your worldview or your interests, you tend to degrade or not to put a lot of importance on it. And what I would like to do today is have your take on skepticism. The importance, first of all, the importance of skepticism in science in general, and should you be skeptical? So there are two things here. One is, how do you view skepticism in science, first of all, right? Second of all, would you incorporate skepticism in your lives, assuming that you are learning science, perhaps for the first time? So should you incorporate skepticism in your life? Those are the 2 points. So there are 2 points. One is general, your view of skepticism in science, how it is important, and the second one is, would you incorporate that in your day-by-day actions based on the fact that you understand it might or might not be interesting for you. Okay? All right. So let me go over this week's subject. Hey, Thor, are you there? You were there. Good to see you. It's funny because usually when a student come by, I hear a click, and I didn't hear this time. So, and I'm taping, so I'm not gonna ask you questions directly, but we can do later. All right, so let me just bring some sharing screens now. All right, so basically, when you think about analyzing starlights, if you don't have the training astronomers do, you think that astronomers go to the mountain and keep looking through telescope to find things. I mean, that is far from the truth. Perhaps in 1800 or before, 1800, that was the case. You would just be looking through the eyepiece and try to make science with it. So nowadays it's different. You use telescope to collect light, and you use instruments that can be kind of organized into 2 broad categories: photometers and spectrographers. So photometers, what they do, they collect light in either in the entire frequency band possible or in a very narrow frequency band. And by doing so, it can analyze fluctuations or variation of the light curve as the star or the galaxy or the system evolves. And that's what photometry do. And spectroscopy does a different ballgame, and that is to take the light and spread out like a rainbow, and then you can analyze emissions or absorption lines on that rainbow and derive stellar properties. So basically what this chapter is all about is to highlight and to give examples on how that is done in astronomy. And I would try to take you to a web page that you have access to where that information is better explained with simulation. So first of all, stellar color. So here I have a picture of a group of stars, and then you can see, I mean, they don't have basically the same color. Some stars are orange or red, and why is that? So one of the main things we can derive visually is if you go in the first half of the night and look at the sky, and then you see Sirius and Betelgeuse, if you can locate them and identify them in the sky, and then you see Sirius and Betelgeuse, I mean, apparently their colors are different. Sirius has some whitish color, electric blue color, that's how it's called. And whereas Betelgeuse is kind of an orange-red. So why is that? So the stars appears bright in the sky depends on its luminosity and distance. The star colors indicates how hot its surface is. So this is Wien's law that is pretty much highlight in this chapter, and in the figure, the top figure on the left-hand side, this is more or less indicated. You have three graphics that show intensity in the vertical direction by frequency or wavelength in the horizontal direction. And then you have the rainbows in there, which are the optical colors. And then you can see the red star. The red star is peaking, which means the intensity curve, most of its flux is peaking in the infrared. In color bands, there are of a wavelength longer than that of the red. And if you go to a blue star, kind of a hot star, 50,000 Kelvin surface temperature, the star itself is peaking more towards the blue. So it has all the other colors, but there is a dominant frequency, like the sun is pretty much centered in the optical range, is centered in the rainbow. And no wonder why our receptacles, our eyes, are very much sensitive to that color band. Okay, so let me go to a first animation here, and that you can find if you Google NAAP Astronomy Labs. It's right there. And then you go to class action, and then you go down, and then you have all kind of exercises you can play with, and then I'll start to use them in a second. But let's go to light and spectra. Animations. Let's take a look of black body. So black bodies in astronomy or in physics are objects, let's see if I can spin there, are objects that have the capability of emitting light at all frequencies, emit light at all frequencies, and absorb light at all frequencies, but does not reflect light. So a black body is a gas, or is a metal, is a solid thing that can it produce its own radiation, and its radiation is not the result of reflecting light. So you might, if you look around in your room, for instance, I have a sign, emergency eye wash, and the sign is written with a background in green. So that green color is not a green color that is self-produced in that environment. It's a green color that is being reflected off the plate because the chemicals in it absorb everything else but reject the green, like the same process that happened on trees. The leaves are green because the chemicals or the process that goes in there absorbs everything else and reflects the green, and then we can see is a green. So a black body is a different, and this animation here, or this simulation, is a good one because it shows a nail, and you have a circuit here. Once we start, energy or current is going to go through the circuit, and as it goes through the nail, it will warm up. And then look on the right hand side, the intensity or the black body radiation of it. So the temperature is growing, and the black body is also growing here. First peaking in the infrared, right? And eventually it's gonna start peaking the blue, but then the metal can't support that anymore and then it breaks down. See that? And now it starts going down. So if I go back there, start again. So it start all dark, but then the metal, because current is going through that in a closed circuit, the metal start to heat up and then become self-luminous. And then we can see eventually as red, orange, bright yellow, and then it can't go anymore. Probably if that were in a star, it would be pretty much plasma vaporized. But then this kind of a high, or gives you some idea of a black body radiation basically is. So if we think about the sun as being a star that has its radiation peaking somewhere between 500 nanometers and 600 nanometers, then you can, it's right, kind of right there. So that's the color of the sun. That's the color of the sun. Now it's too much, right? And that's what we see. You guys want to say something about this? Oh, okay. So let's go back to the PowerPoint. Now, the other one is luminosity. And it's important that we learn to differentiate what luminosity and brightness are. So luminosity is a quantity that measures the amount of energy that comes out of objects. So luminosity is intrinsic energy. Sometimes it's called intrinsic brightness of an object. Like stars have its own luminosity, which means if you go around them, if you could, and then you measure the entire energy they are sending out and divide by their surface area, then you have a measure of luminosity, how much energy that star is sending out in space. Now, brightness is different. Brightness is what you receive, and that depends on how far you are from these objects. Like if you go in the night sky and then you look up to the sky, you are going to see stars, some of them pretty bright, some of them not so bright. So does this tell you how luminous they are? Does this tell you how far they are, how close they are? Not at all. So in general, luminous stars, those who have a lot of energy, intrinsic, they are huge, they have a large surface area producing and emitting energy. So those stars are those that you're going to see more prominently at nighttime. And stars that are not so big, even like a sun-like star, it will not appear so luminous. But luminosity is how much energy the star itself sends out, and brightness is what you receive here. Okay. The other key aspect of this chapter is stellar spectrum. So a stellar spectrum can tell you lots of information about star. For instance, depending on how hot the surface is, and we can tell by photometry, like by comparing colors of star or doing what astronomers call color indexing, which is comparing the color of the star in two specific color bands. But spectroscopy, analyzing the absorption lines or certain kinks or emission lines, certain transitions show. By doing that, astronomers can tell how fast the stars rotate, can tell how fast they are going towards or away from you. It can tell what's the chemical abundance of the materials in there, and also temperature, because depending on if the star is too hot, it will ionize the gas more efficiently than it is than it would happen in a star that has a much lower surface temperature. Stars that are like this red star in my diagram here in the left-hand side, stars that are cool stars, they tend to have a lot of molecules because the temperature in the gas is good enough to allow atoms now to combine, forming molecules, as opposed to stars like the blue star in there is so hot that there are no chances of molecules being formed in the atmosphere. Most of the gas is ionized, and so the spectral signature you collect is completely different. So temperature, chemical abundance, rotation, receding or approaching velocity, all of that we can get. And in general, what we found, and that was found in the 1800s, that most of the stars are hydrogen and helium, which means if we take all the stuff the universe is made of, not including dark matter, not including exotic things like dark energy, but material that we see and we can account for, most of it is hydrogen and helium primarily. Stars are 75% of hydrogen and 25% of helium, basically. Let me go back to that animation, and let's take a look at spectrum. Now, let's say you have a spectrograph, and the spectrograph, what it does, it creates a rainbow. And see, if we try to do that in the laboratory, I mean, we can do with a piece of glass, we might be able to see a rainbow, but you can use good technology to make a decent, very well done rainbow like that. So this is the so-called continuum spectra. Like if you take the sun and make the sun be a perfect black body, radiating at 6,000 Kelvin, that's what you see. Now, if you add hydrogen to the gas surrounding the star, this is what you got. So the sun, if you observe the sun, and the sun, let's say, just make an example, if the sun were a star of pure hydrogen, this is what we would observe. Now, if you add helium, not a lot of thing going on in there. And the reason is helium requires very hot environments to appear. Now, if I change this slide bar to a hot star, see that? See those lines appearing there? Those are helium lines. And if the star is very hot, like an O star, you do not find signatures of hydrogen anymore, although hydrogen in there. See that? And if you probe, if you do spectroscopy over a cool star, like a B star, or somewhere between a B and an O, you might have hydrogen and helium signatures. It doesn't mean the star doesn't have hydrogen. It does have hydrogen, but it's all ionized, and you do not see those transition lines. Like for this very hot star, I can add metals. I can add, as I just did, I add metals, and I add, let's say, carbon, magnesium, zinc, vanadium, titanium, but nothing happened. What if I add ionized metals? Nothing happened. What if now I reduce the temperature of my target star? Let's say I observe the sun. It's a G2 right there. Oh, almost G4. The sun. Oh, the sun is a G2. Let's keep it there. See all these blue transitions here? So those are ionized metals or metals. They present signature in the blue part of the spectrum. And if I add my observations towards cooler members, like Betelgeuse, so my ionized, my high frequency lines, transitions disappear because the star is too cold to provide enough energy to excite the metals to the point that I can see transitions. So astronomers, when they trace a star that has this signature, so the only element for a K2, yeah, hydrogen. So hydrogen in there. So if you do to a K2, you can barely see it. You might see some, but it's barely. It's very, very narrow. Now, what if you add molecules? Ooh, now I can see molecules, especially if you go to lower temperature. Now molecules will appear. How about ionized? Nothing. How about helium? Nothing. How about ionized helium? Nothing. So the main point here in the spectrum, we know that stars have primarily hydrogen, a quarter part of helium, and trace amounts of everything else. But to trace their absorption, to trace information on how abundant those metals are and how the star rotates, a rotation rate, and receding or approaching velocities, you must be able to do spectroscopy at a higher resolution, as we say, and then we can see all of that with more details. So when do you have emission lines? When do we have absorption lines? When do we have continuum? So let's say you have let me see how I can do that. Here you have a spectrometer. I have to find out how to use this. Okay, I'm going to bring my telescope and point my telescope towards the black body. An incandescent light bulb can work like a black body radiation, which gives a display of light intensity at all possible frequencies, right? So this light bulb is shining on this cloud. So if I bring my telescope and place it in here, so I do have both. I have the black body, which I had before, but now radiation that goes from the light bulb passes through the cloud. The cloud has hydrogen atoms, supposedly, right? It has hydrogen atoms that will selectively absorb at exactly those frequencies, and as a result, we see a combination of both effects: the black body from the incandescent light bulb and the cloud. Light bulb is not a light bulb, but is the hot central part of a star. And on top of this hot central part of the star, you have the stellar atmosphere, which is a thin layer. In the case of the sun, so just for comparison, the sun is a star that is about 100 times in diameter bigger than Earth. So it's kind of a big thing, right? So Earth is big, so take 100 times that, is really big. But the atmosphere, the solar atmosphere, is 1,000 kilometers. In fact, the region where most of the radiation comes out is 400 kilometers, which is 300 miles. 300 miles, it's very thin. That's where the region where radiation escapes. Is a cool region that overlies the hot interior part. So when the radiation, the black body that comes from the internal part, migrates and passes and diffuses through the atmosphere, it brings with it signature, and that's what you detect in your telescope. And then you have absorption spectra, and then students and astronomers can take the spectra and spend a whole year just analyzing features on those lines. Now, if you take now your telescope and you put in a funny position, which means you look at the cloud alone, see that? But eliminating the background star, then you are seeing part of the radiation that is being sent out by the star itself, by the cloud itself. See, when atoms absorb radiation and forming these dark lines, so imagine again, so you have a black body, so that black body, in certain frequencies, the radiation was taken out because atoms kind of sucked that in. They took that energy out. But the atoms don't stay with that energy all the time. They stay for a very short period of time, and then they send those frequencies, those photons, back to the space, but not in the same direction they were going. Once an atom take a photon out of the light beam and get excited, when this excitation takes place and that radiation goes out, it goes out in any direction. It doesn't go exactly in the same direction it was going before. It's like the atom loses memory, or the photon loses memory of where it was supposed to go. And which means the cloud itself is like a center now, radiating transition or photons in any given direction. So if you get out of that black body, right here, for instance, oh, I didn't. How come I'm not being able to? Oh, there you go. So if you put now your telescope directly towards the cloud, those photons that were being sent to any direction now can be seen in its emission aspects. So those are emission lines, and those we saw before were absorption lines. The same elements, hydrogen, and if you look directly towards the black body, you see none of them. Okay. Very important, Doppler shift. I have some animation. The Big Bang Theory had a segment on black body, a Doppler effect, with Sheldon explaining what Doppler effect is. Doppler effect, it happens when there is a relative velocity between the source and the observer. So when there is either the observer or the sources are moving to one another or moving apart, the frequency the source emits is not the frequency detected. There is always a small shift, so that if both are moving towards one another, the frequencies shift towards higher frequency. In other words, it's blue shifted. The wavelength is blue shifted. And whereas if they are moving apart, the frequency migrates towards a smaller frequency, or what we detect a redshift. So let me start animation. So we have a source that is producing waves. Let's be a little bit more dramatic here. Let's increase the frequency. And the observer. The observer is right here. The same wavelength that is coming out of the source. Now let's move the observer towards the source. See what happened here? The frequency, the wavelength is shorter than it used to be. And if you move that way, in fact, if you match the frequency, look what you get. The wavelength is bigger, so you have a red shift. So blue shift and red shift. So the equations governing this effect are very well known by physicists and astronomers. And so when we observe anything, we are on a planet Earth that is spinning, right? And this planet Earth is going around the sun, so we have a revolution going on. And the sun has also its own motion, because it's not in the center of the solar system, but is being tugged by Jupiter, Saturn, and all the other planets, and the sun itself is moving around. So when we measure what we call a red shift of stars, we have to take into account all these different motions, so that we know for sure how, if the star we are observing is going towards us or away from us in respect to a certain reference frame. But basically, that's the technique Doppler effect. So Doppler effect can be used not only to give us speeding tickets, the same technique, except that the highway patrol use a infrared light beam that goes towards the car, reflects back, and then the frequency detected is slightly different from the frequency he or she sends. And by combining those two quantities, you can get with high precision the speed of the car. In the case of stellar objects, we don't send signal to the stellar objects. We just wait the light to come, and by doing so, we can detect receding or approaching velocity. This can also be used in cosmology. So how do we know the universe is expanding? There is a universal expansion and now acceleration of the universe. Well, because we observe galaxies, and galaxies are in space. And the space that lies between us and these galaxies that are being observed, this space is stretching. And then we measure that stretch using Doppler effect. It's the same idea, except that we have, or the same technique, except that we use cosmological Doppler effect to indicate that's not the object itself or the galaxy itself that moving at those speeds with respect to us, but it's the space itself that is controlling the effect. This is a simulator that shows how, in fact, last week discussion we had a discussion on exoplanets and the two major techniques used to find these exoplanets. So, and then you guys wrote, and I think I got very good feedback. You guys wrote me very good feedbacks. I'm very happy always. I always learn something new when I read your reports. So on the two techniques, photometry, pretty much Kepler, satellites, spectroscopy, pretty much several different groups. In fact, the first planets detected were done using spectroscopy. So you have several reference lines, and those reference lines are used to measure standard motions of star with respect to it. So let's see an animation here. You have a star and you have a exoplanet like a Jupiter-sized planet, let's say, that's giving a big tug on the star itself. Remember, Kepler was able to detect solar type, in fact, Earth type planets, planets that don't have enough mass close to the star, that doesn't give a lot of a tug to the star, right? And how did Kepler detect them? By finding how much of the light of the stars were being dimmed by the passage, by the transit of these Earth type planets. Now, Jupiter-sized planets can be detected not only by Kepler technique, by photometry, but can also be detected using spectroscopy. Spectroscopy will not be efficiently used to measure Earth-sized planets because the tug on the star is not that great, whereas Jupiter's size gives enough tug. So what you're going to see here is the Jupiter-sized planet doing a pirouette with the star, and the star is not in the center of the system. It's kind of off, and it's going around wobbling because the planets go around it. So let's take a look and see what's happening. So the planet's going around, and you see the star, which is right in the center, kind of going around in circles. So take a look at the spectrometer. Of course, the shift here is exaggerated, so the shift is not that great, but you can see the shift on few important lines as a result of the motion. So now the star is going towards the observer, and the star is going away from the observer. So you have the blue shift and you have the red shift right now. And then the blue shift, and now the red shift. When the star is going parallel to or perpendicular to the line of sight, then you are in the middle of that. So you don't have shift. You have the standard frame. So this technique was used by observers and astronomers in different sites that pretty much rely on spectroscopy, basically. Okay, this is spectroscopy, basically. And again, Doppler effect. Doppler effect to find, as a tool to find planets. What apparent magnitude is? So we saw there is a distinction between luminosity and brightness. Now, brightness is converted or was converted using a logarithm scale to what we call magnitude or apparent magnitude. So apparent magnitude is a scale, a logarithm scale that converts these big numbers or small numbers in brightness as we observed and convert them in a scale that we can manipulate and talk about it. In this scale, what is interesting here, and this you should know, is that smaller the number is, the brighter the object appears in the sky. Like, look at this. The sun, which is the most bright object in the sky, has an apparent magnitude somewhere between negative 25, negative 30. And what is the limit to what we can see is about 6. 6. So a star or an object magnitude 7, we can see it. Whereas Sirius or these bright stars are of a negative magnitude, as you can see in there. The full moon is quite of a bright object, has a magnitude of negative 13 or so, negative 14. And the Hubble can see up to magnitude 30. This is so faint that you require a telescope, a space telescope. So more about stars of different colors. Now, spectral classification was primarily done by women, in fact. This is a rainbow. Remember what I saw before, just one rainbow. With the CCD technology, you have the ability of creating rainbows in 2 dimensions, and you can go. Oh, this is not a CCD spectra. I'm sorry. This is a bunch of spectra putting together on a sequence. Sorry. So what is being shown here, if you look in the right-hand side, you have the hydrogen line that becomes stronger in the star of spectral type A, right? And becomes very weak as you go to a star cooler than the sun. And in a B star, this hydrogen line disappears. This is to show that you can classify stars depending on the intensity of certain absorption lines. And this classifications was done by several women working in the 1800s by Pickering. And here's the picture of them, the Harvard group of Herren. That's how they were known. So this guy in the center, Pickering, he had his postdoc doing the work of spectral classification, which is pretty much getting those transitions and try to identify, the elements and try to make some sense on it. But they were taking too long, and then Pickering said, well, I can pretty much hire my maid, and and she could do a better job than you guys. And that's what he did. He hired Wilhelmine Fleming, and then after that, others came by, like Annie Cannon, Cecilia Payne, and they did the entire classifications as we know today. So they classify stars based on hydrogen lines because they were easier to find, and they call star A those stars with the strongest hydrogen line, and then star B, C, D, so on, so on, so on. And then later on, they changed classifications. They put numbers in between those letters when the technology improved the spectrographs. And then we have the stellar classification as we have today, O, B, A, F, G, K, M. And then you can memorize by saying, O, B, A, fine girl, kiss me. Or O, B, A, fine guy, kiss me. Depending on what you like. And there you go. And the stars are, again, you can use their spectral signature to address them. Now, what proper motion is? Proper motion is once you know and once you can use Doppler effect, and once you have enough spatial resolution to measure parallaxes, you find that certain stars are so close that they have, and you have a measurable what's called proper motion. What proper motion is, I think I have a figure of it. Yes, I do. So a proper motion is this. When you use Doppler effect, which I just saw or just show you in the animation, when you use Doppler effect, you can measure what in this figure is called radial velocity, which is the velocity of the star with respect to your line of sight. So if you take a line from the sun or from planet Earth to the star and extend that, so Doppler effect allows you to measure the velocity of the star projected along that line of sight. So if you go towards you, you have a blue shift. It goes away from you, you have a red shift. Now, when you observe the stars in the sky and you are able to measure how fast the star moves in respect to stars that are even further, then you measure on a certain time length, you can measure their transverse velocity, right? Which means the star keep changing position with respect to stars that are even further out. And if you do that over a certain period of time, you have the transverse velocity. When you combine two, you have the spatial velocity of that star, basically. So when you combine these two vectors. And that is the so-called proper motion. So Barnard is the star that has the largest proper motion you can get. Also, in this picture, it shows that Doppler effect does something interesting. And that is to allow astronomers to measure how fast the star spins around its axis of rotation. So if you take, and now goes to the details, right, that require spectral resolution. And nowadays you can buy a spectrograph and put in your backyard telescope and get all kind of a cool information. You spend a few $1,000s, but if you are a nerd in astronomy, that might be something cool to do. And here's an example of what you can do with it. Usually a star that's not rotating fast has a line that is the one in the left-hand side, has a narrow absorption emission. But if the star rotates, Doppler effect will smear this line and make it broader like the one in the right-hand side. So astronomers can use a very simple technique by artificially rotating a template line and try to match the line that is observed. And by doing so, you can indicate what is the rotational rate of that star around its axis of rotation. So again, it's another information that can be derived using spectroscopy. Some stars rotating very fast, 6.5 hours, like the sun takes 25 days to give a rotation. What is... Oh, this is about, remember the animation that I showed you with the star and the planet? The star was not exactly in the center, but both of them go around what's called center of mass of the system, is where the system is balanced. And astronomers can calculate that using pretty much Newton's law of gravity. And so if two stars, if you have a binary system rotating, you can observe them, you observe that system, and then you see two of these absorption lines moving in respect to one another. And by finding out how these sets of lines restore their original configuration, you can determine how long it takes that system to complete one turn. So those types of binary systems are called spectroscopic binaries. Some spectroscopic binaries, sometimes you don't see them resolved visually, which means you take a telescope and then you observe them but they are so far away you cannot see those two stars separated because they are too far and you can't resolve them independently. But with spectroscopy, you can. You can see those two lines moving and migrating around a common center, and then you can determine with that information what type of star it is a K, is an M, is a O, F, what is it? Because depending on the lines, and you also can find out how far they are based on the rotational period of it. And that is the radial velocity curve of both stars that astronomers can use to further infer physical properties of stars. Now, when astronomers collect information about distances, so Cecilia Payne, one of the women that I showed previously, she was fundamental in helping to extend the ruler the astronomers use to give distance to celestial objects, and by pretty much 1800, beginning 1900, we had good precisions, good technology, good tools to establish distance to the stars, and so we could pretty much, based on their brightness, since we know the distance, we could get their luminosity. And then it was found that certain stars obey this ratio, which is very nice, you can see perfectly here, of their luminosity by mass. So based on the luminosity of the stars, you can estimate their mass, their content, basically. And so there is a relation, mass luminosity relation for stars that are for which their properties are well known. You can think that mass is energy, right? And luminosity is energy. So it's not so surprised that this correlation exists between mass and luminosity. So more massive the star is, more luminosity it should produce and send out to the space. And less mass implies less energy, and less luminosity would come out. Again, luminosity is a measure of energy. Photometry allows, we saw photometry in the realm of exoplanet, but it was first extensively used to address the fact that more than 50% of the stars in the sky are binary systems. And sometimes they have 3 members or 4 members, quadruple systems, 4 stars going around a common center of mass. And you can use photometry to not only indicate the mass of the stars, the size, and their evolutionary status. So there you go. Oh, this is another simple thing you can do in the classroom. So, and I would like to close this week with the Hertzsprung-Russell diagram. Now, imagine that now by beginning of 20th century, you have a nice information about luminosity of certain stars, or several stars are there, because you know you can measure their brightness, and you know their spectral characteristics, and then you know how much of their energy is being sent out. You might perhaps find indications of their sizes, and then you know the luminosity of these objects. And then by observing either photometrically or spectroscopically, you can address their surface temperature. And when this is done, you create a graphic which is commonly referred as Hertzsprung-Russell diagram, which I'm showing here to you. So the HR diagram is a core material, core subject in our course. So the HR diagram, once you place all the stars you have in the sky and information about them in there, what you'll find is something interesting. More than 90% of the star happen to be located in this line that goes across from lower right-hand side to the upper left-hand side, from lower red to upper blue. And those stars, those dots are called main sequence. And if you observe closely, our sun is a main sequence star. See that right in the middle of the graphic where the yellow is. So sun is a main sequence star. Several stars are a main sequence, but you have 5% or so of stars that are called giants. And you have another smaller percentage of those called supergiants. They are very big out there. Um, and you have a small group of members in the lower left-hand side in the blue part of the spectrum, which is pretty hot, called white dwarfs. So what those stars are? Well, once you study evolution of stars, and that's what going to come in the following chapters, you realize main sequence stars are those that are called mature stars. They are undergoing fusion reactions in their very core. Hydrogen is being fused into helium, energy is being generated, the stars are kept kind of stable over a long period of time. But eventually that fusion reactions will be exhausted because hydrogen, which is fueling this process, is going to be gone. It's going to be converted to helium completely. As a result, changes will occur in the star and stars will become either supergiants or giants. And that those little dots you can see up there represent stars that are in a process of dying, in a process of moving out of the main sequence and eventually undergo further process. In the case of stars less massive than 8 solar masses, they will become a white dwarf, and that's what you see in the lower part of blue part of this spectrum. And some stars that are more massive than 8 solar mass, they might end up their life cycle in what we call a supernova explosion, leaving as a result, remains as a corpse, a neutron star or a black hole. But this is going to be explored in the next segment of our course. So yes, HR diagram is important and is an evolutionary display of stars. So if you can observe a star and if you can determine its surface temperature, if you can use independent means to have an indicator of its luminosity, once you plug in this diagram, you can pretty much tell in which evolutionary stage that star is. Is it still as a main sequence, or is kind of a dying out as a red giant, or what's going on with that star? Okay, so this is, but primarily the point of this chapter is to show that you can pretty much use all kind of techniques to basically photometry and spectroscopy, plus a lot of theory and knowing how light is and how physics govern the nature, basically the laws of physics govern nature, to figure out what's going on out there. Okay. So do you guys have any question before so let me just stop taping now.